So this is stuff that you have to do. I am not going to sit here and talk too much about it. Scientific method. Oh, sorry, did you get that? I'm going pretty fast because I'm recording it. 1.1 and 1.2 are the sections that you need to just read and understand. Okay? And there's problems in the homework. You saw there's problems in the homework to test whether or not you understood it. It's not stuff that you have to toil over too much. You'll figure it out. Okay? I trust you guys on that. The one thing I do want to say is this. Your book does a really good job of distinguishing between a law and a theory. I could let you just read all about that. But basically, a law, two characteristics. It doesn't explain anything. But it does, right, give the relationship between variables and an outcome. Oops, the internet's a little quirky here, so sometimes I skip. I'm not going to go over the scientific method. I'm sure you guys have seen this in other science classes if you've taken it. But basically, a law doesn't explain anything. So everybody thinks, oh, if it's a law, it must be like the biggest deal ever. Turns out the biggest deal ever is probably a theory. Okay? A theory actually explains. It actually explains why things happen. So when somebody says, oh, that's just a theory, that's actually the highest level of understanding that we have, right? Now, in common language, that's not true. Oh, you just have some, because we're always conspiracy theory. You know, it's just one of those theories. That's kind of okay in that context. But in science, when we say it's a theory, that means what's happened is lots of experiments have been done to try to understand the relationship between the variables and the outcomes, so you understand the mechanics of how things work. Okay? So that's the big distinction there. You might not get that in reading it, but your book actually is one of the only books I've ever read that actually does a good job of that. Okay? So you can go through and read all that stuff. Okay, so let's talk about states of matter. I printed out my slides so I could look at them as I went along. Sorry. Just getting myself organized, first date kind of things. And we're still recording, so that's good. All right, so states. Same substance, three physical states. This is the ones we talk about in the early part of the class. Later in the semester, we'll learn about other kinds of states of matter. There's actually 5 states of matter. The 3 physical states that we typically talk about are the solid, the liquid, and the gas. Right? Let's see. Think about water. And you have 3 physical states for water. Okay. What are the physical states? What do we call them? Vapor, steam. Vapor is probably a better word. Ice, right? And water. We call it water, right? But water is H2O. And all those states, okay, they're the same substance. It's always H2O. Okay. What's different about each of those states? Yeah, so exactly. So the difference is the amount of energy that's in the states, right, versus how much attraction the molecules have for each other. So physical states, we think about solid, liquids, and gas. Solids, if you think about a picture of solid, liquid, and gas, The solid, this is solid oxygen, the crystal structure for solid oxygen. When you can get oxygen, the air we breathe, you can get it to be in solid form. It kind of looks like that. The colors are a little distorted, unfortunately. Makes these nice O2. You guys know oxygen, the air you breathe, is O2? Right? Makes this nice little crystal structure. The molecules sit there in a crystal lattice and they vibrate, but it's at a very low temperature. It's about, if you did it in Celsius, it's about minus 220 degrees Celsius. You don't see that very often, right? 50 degrees Kelvin. On the other hand, it can go to the liquid state, right? And what happens is from the solid state, they're close together, they're vibrating, they can't move. They're stuck together except for they vibrate in place. And then what happens is as you put more energy into it, it's kind of like if I brought a pot of coffee in here. I have Death Wish coffee. You ever had Death Wish coffee? This stuff's brutal. It tastes great. Yeah. But if I put a pot of Death Wish coffee out here and you all had a cup, right, a sip of it, your energy would go. You might not move out of your chair yet, but then eventually you would start like, I can't sit down anymore. That's what the liquid is. Right? The amount of energy is higher, temperature is higher, right? Energy is higher, and things begin to move, but they're not so energetic that they have to leave. Now, if I brought in a giant pot of Death Wish coffee, right, then what happens is you guys can't stand to be next to each other. You'll have so much energy that the force of attraction, the thing that's holding in you in this room, like the door, right, won't keep you in place, and you'll just all leave. Okay, so we think about this real quickly. If you're thinking about the states of matter, right, and I'm not going to go over this in a lot of detail because a lot of this is review. Solid is very dense, right? Has its own shape. That's why we call it a solid. Right? Not very compressible because why is it a solid compressible? Solid. It's a solid, but that's kind of like the observation. Oh, all these solids, I can't compress them very well.
Because the attraction between them is very high.
That's related, but that's not it.
It's already compressed.
It's already compressed. They're already really close together, right? Like it's a solid, there's no space in between. But like a gas, you know you can take a gas and you can compress it. You can compress a gas all the way down into a liquid. Okay? So why can you compress a gas? I mean, just look at the picture, what it looks like. The molecules are what? They're far apart, so there's a lot of empty space. It's kind of like, you guys don't think about this maybe, but I think about these things all the time. It's like the solar system. Do you guys realize, like, if the sun is this big, right? The earth is this tiny little grain, and it's like all the way to the end of the hallway. And the rest is empty. That's what this is like. You've got all these little planets and nothing in between them. So it's easy to take them and just squeeze it down until, in fact, they become a liquid. You can actually force them back together. Okay? Not always, but you can. Okay, so that's all I want to talk about, physical states of matter. We're going to talk a little bit. So chemists like to organize things. States of matter is just one of the ways we organize stuff. The other way we organize stuff is by talking about whether something is pure or a mixture. Okay? And Chem 3A, I spent 20 or 30 minutes on it. I'm almost done. Okay, so if you haven't had the prerequisite, by the way, we do have or you don't get into this class, there's a late starting 101P. Our 101Ps generally start after the beginning of the semester. So students who don't get into it, don't have the prerequisite, or haven't taken 101P and just want to stay on top of chemistry can take that class. Even if you took 3A, you can take that class. Okay, okay, so we'll talk about pure substances. We're actually going to start at the bottom of the chart. And we're going to look at atoms, okay? I'm assuming you guys know what our atoms are. We give all the atoms symbols, and we put them on the periodic table. So hydrogen is the smallest of the elements. And probably I don't know if we have 118 yet, but I thought we had 117. But 116 on this periodic table, well, actually, the asterisks on these means they've been made. We're not sure. Okay, but it may be that they're sure now. Okay, I don't know for sure. That's weird. Okay, that would be the heaviest, the largest element that we know of, but that one's man-made. It doesn't exist in nature. It's too unstable. Okay. So that we list all of the elements on the periodic table, individual atoms of those. Okay. These would be pure. On the other hand, I could combine these, right? So I can take an atom, A, and combine it like this, and this would be known as a diatomic. We'll talk about that. But if this is all that you had, that would be pure too. Okay? But if I took A and B together, same thing. If I made a compound, what do you think compound means? More than one element. A combination of two or more elements. Okay? So again, these are all terms that you need to know. Compounds are combinations of two or more elements. This is also pure. Even though it has two different things in it, the compound always has the same formula. So like when you drink water, what are you drinking? H2O, right? Doesn't matter where you drink the water. If you're on Mars and you're drinking water, that's cool and everything, but it's still water, right? If you're at the bottom of the Mariana Trench, 100 atmospheres of pressure, you're still drinking water. You're probably dead, but you're drinking. That'd be a good trick. That's a lot of pressure, by the way. Not much can go down there and be okay. Now, so let me point out really quickly, there's different kinds of elements. And I'm just going to point this out very quickly on this slide. These are known as, the ones on the right, these are atomic elements. Most of the periodic table are atomic elements. Iron, copper, lithium, magnesium. Those mostly made up of atoms. When you get pure magnesium, it's just made of magnesium atoms. They sit roughly in a crystal structure, a lattice, like I showed you for oxygen just a second ago. That's mostly what they look like. Then what we have is we have what we call the molecular elements. I didn't know where I was going to fit this in when I was putting the slides together, and I just discovered, hey, I'll just put it in here. The molecular elements are the, so it's over here. These are molecular elements. Those are elements that when you find them in nature are combined with atoms just like themselves. So an element is composed of only one kind of atom, okay? But you can have either atomic elements, which are atoms, or molecular elements where atoms of the same type get together. So the type that we are most commonly acquainted with are known as the diatomic elements. Okay. Anybody remember which ones they are? Hey, cheater. You memorized those. Yeah, it's the seven. The seven that make the seven. All right? So if you look on the periodic table, this is my idea of a high-tech pointer. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and the last one? No, we don't know much about this hydrogen. We assume that it is. Do you know how much of this there is in the earth? Like a gram. In the earth. Yeah, we don't have much of it. So it could be. I don't know.
Isn't that one of the most rarest elements?
It's one of the rarest elements. You'll notice that these have parentheses on their molar masses, their molecular weights. We're getting a little ahead of ourselves, but you guys are probably familiar with that term. Their masses are in parentheses, right? That's because there's no stable isotope. They all decompose.
Yes, it's just too unstable for it to have to go past more
Yeah, it hit the mass. It's above the mass limit for a stable nucleus, and all those nuclei, like you see where bismuth is,
Yeah.
beyond bismuth. Shouldn't say all, because I think there's one or two exceptions, but almost all the elements that are past bismuth are unstable. So they all occur, if we have them in nature, they all occur from the decomposition, the nuclear reaction of heavier isotopes of other elements that give us those. Okay, so back on track. Hydrogen's the other one. So the diatomics. So I was going to point out to you, and I'm going to write them on the screen real quick. Hydrogen's one of them, so we'll count one, and then we'll go nitrogen. That's 2. Oxygen 3, 4, 5, 6, 7. So it's the 7 that make the 7. What do I mean by the 7 that makes the 7? Look at the periodic table, the shape. It's a 7, right? So the diatomic molecular elements are hydrogen. You guys say them for me. Otherwise, I have to keep looking up. Nitrogen. Chlorine. Iodine. So by diatomic, we mean they come in nature as 2s. Okay? Now, they're pretty unstable, so you don't usually find them in nature that way, but if you find their elemental form, they'll be I2, O2. So when you're breathing oxygen, right, in air, oxygen in air is about 20% of the air. The rest of it's nitrogen. You're breathing them in as O2 and N2. And anybody know what the rest of the air is made of, mostly?
Well, you have
Huh?
CO2. Well, you have oxygen, CO2, nitrogen. You have carbon dioxide, of course. Methane is.
Yeah, but what's the remaining most of the 5% that's there?
Helium.
See, you're having a hard time thinking what it is.
Sorry.
No, it's okay. For many years, they didn't know what it was. And they had to figure it out through experiment. A guy named Ramsey, University College London, figured it out. It was one of the first noble gases that was discovered. It was argon.
Argon.
Yeah, argon makes up a fairly significant portion of our atmosphere. And the name argon means the lazy one, because he couldn't get it to do anything. He could get all the oxygen to react. He could get all the nitrogen to react.
It's inert.
Yeah, it's an inert gas. So he had this gas. He couldn't get it to react. So they named it the lazy one, because they didn't know what else to do. And then subsequent to that, they figured out there was a whole group in the periodic table that was missing, and they filled it in. It's a neat story, if you like history kind of stuff. Okay, so these are all, down here, these are all pure substances. You get elements that are atomic, you can have compounds, but if they have to be by themselves, but as soon as you put them together, they're a mixture. Okay? So there are two kinds of mixtures. There's the homogeneous mixture and the heterogeneous mixture. What does heterogeneous mean?
Means that the mixture's kind of rough. They're different
Same
size.
exact type of mixtures, like the same everything. So if it's oxygen, then oxygen's heterogeneous. Sorry, it's different.
No, that's homogeneous.
Yeah, we're doing
I'm
homogeneous.
sorry.
Yeah.
Yeah, and the example they give, I think, in the homework and everything is it's like comparing beef stew to like tea.
Yeah. Beef stew versus tea is a great example. It's in the homework? Awesome. So,
Well, it's in the course text.
Yeah.
It's in the textbook. Yeah.
so, but if it's coarse, if you think of it as being a rough mixture, it's not the same all the way. So hetero means different, right? So it's not the same all the way. So that's the good example of it. I always do chili verde and rice, because that's like one of my favorite things to eat, right? And I started a little early. I usually don't talk about food till 11 o'clock, because then I get hungry and I can't think about anything else. So, but chili verde and rice, right? It's got beans in it. It's got chunks of chili verde in it, of the pork. It's got the seeds from the tomatillos. It's got all that stuff, but it's not homogeneous. On the other hand, tea, clear, it's the same all the way throughout. If you put sugar in it, it's the same sweet at the top as it is on the bottom,
Well,
right?
milk has to be homogenized.
Yeah, milk is kind of not really homogeneous. It's really kind of heterogeneous. If you look at it, it's got globules in it of fat that float around. But anyways, that's another long story. Okay, so mixtures are homogeneous versus heterogeneous. So that's just another classification. So we have classifications of state, solid, liquid, and gas. We have classifications based on composition. Either it's a pure substance or it's a mixture, and then mixtures are either homogeneous or heterogeneous. Okay? Okay. We also like to classify other things. So we have physical and chemical changes. So a physical change is a change that occurs without changing the substance. It's the same stuff. So this, I was going to take a piece of chalk, but I want to get a piece of chalk that I don't care about. I'll just use this one. That's a piece of chalk, right? That's a piece of chalk. It's many pieces of chalk, right? That's a physical change. It's still chalk. When water undergoes transitions between solid to liquid and liquid to gas, same stuff, those are physical changes. If I took a diamond ring, hit it with a hammer, made diamond powder out of it, that would still be a physical change. It'd be a very sad one. Okay? So things that change without changing the composition of the substance, those includes the phase changes when you extract something out of something else. Okay? If you sift things, like if you're an archaeologist and you have artifacts like they dig up in these old Roman wells where people used to throw things in, right? There's a lot of sediment in there, and they take a metal screen and they put all the diggings from the earth on the screen, and then they shake it gently, and all the small particles fall through. The small particles were small particles above, now they're small particles below. That's a physical, right, separation, a physical change. Crushing, like I talked about diamond, that would also be. Now, we also talk about chemical changes. Chemical changes occur when you make something new. Okay? So if you start with something and you end with something that's different in its composition, that's a chemical change. So you've got to make something new. So burning, like you take a wooden log, I don't know what other kind of log you have, I suppose, but yeah, you take a log and you light it on fire, what do you get? Smoke? Ash? Yeah, it's a combustion reaction. You get stuff, but is there wood left when you're done? No, that's a chemical change. You made something new. Okay? You also people used to believe in this stuff called caloric. Okay, it's not there anymore. We know what it is now. I'll talk to you about it a little bit. But caloric, for a long time, everybody believed this thing called caloric, this fluid that would come out when you burn stuff. And it was from the phlogiston. That was awesome. Good stuff. And we think it's all crazy now when we talk about it as scientists. It turns out when you look at the papers, you go like, oh, yeah, I do. I guess I believe them. That's pretty cool. And then you realize, no, that's all wrong. Right? They were actually pretty convincing in their arguments. So burning, cooking, like when you take an egg and it goes from being a liquidy substance to a solid white with a solid yellow in the middle, right? You're actually changing that chemical composition. Things that decompose, right? Like the cat under your doorstep. I remember those days when I was a kid on the farm, like, oh, there's that smell under the house. Somebody's got to go under the house and get that animal out. Yeah. And for some people, burning and cooking and decomposition, they're all the same thing. All right? Oh, kimchi. Everybody ever had kimchi? Right? Yeah, kimchi's great stuff. But you take cabbage and garlic and a bunch of spices and you bury it in a pot in the ground. It's good, though. I'm not going to argue. Sorry. That's my inner Asian coming out. Okay, so enough of that. Now, so we have physical properties. Physical changes, nothing new made. Chemical changes, something's new made. And then we have properties that go with those. And you observe the property when you see the change. That's the simple way of putting it. You observe a property when you see the change. So if it's a physical change, there's some physical property associated with it. Okay? So, for example, when you melt something, solid to liquid, or you go the other way, liquid to solid, you freeze something, right? That's a physical change. That happens at the melting point. So when ice freezes, it freezes at 0 degrees Celsius. When it melts, You know what temperature it melts at?
100 degrees Celsius. No,
Melts. Melts.
Oh, melts. 0 degrees. Sorry, I think boil.
Turn your brain on.
0 degrees.
0 degrees Celsius. The melting point and the freezing point, two names for the same thing. It's the same temperature. It's just one is for melting, one's for going to the liquid state, one's for going to the solid state. So one of the things you should have recall from introductory chemistry, melting points, freezing point, same temperature. Okay? Also, you can boil something, all right? And at its boiling point, it boils at
100 degrees.
water, 100 degrees Celsius, and when it condenses from steam, it condenses at 100 degrees Celsius. So at those phase changes, we have these very interesting properties. They're known as intensive properties. So what is, there's intensive and extensive. That was the first question on the homework, actually. Intensive property is something that doesn't change with the quantity, and an extensive property changes with the quantity. So it doesn't matter how much ice you're melting or how much water you're boiling, the temperature is still 0 and 100 degrees Celsius for both. On the other hand, when we talk about mass, right? How much does something weigh? I hate putting those words together, but when you weigh something, when you mass it on a balance, right? How much of it you have changes the number you get. So mass is easily something that we call an extensive property. It depends on how much you have. Not my shirt. His shirt is black. Does it matter how much of his shirt he has? No, it's still going to be a black shirt, right? So that's an intensive property. Now, if I cut his shirt in half, you'd have half a shirt. The quantity of shirt is an extensive property. I'm not going to do that. You can leave your shirt on. He was like, kind of wanted to take his shirt off. It's kind of hot in here. Oh, so I went to, this guy's John Fuller, Fuller Brewery. This guy's name, put it in the slide so I wouldn't forget it. Derek Prentice. So I went to England and just thought it would be fun to show you this picture. This is a mash tun. So you guys, did anybody here make beer at home?
Not beer.
Brew? You distill?
Little. I do
Something,
other stuff.
as long as you can talk about it. Don't.
Well, I don't sell it.
That's kidding. So this is when they make beer at Fuller Brewery. Now Fuller's is one of the largest breweries in England. So I went to go visit, and he is like he used to be. He retired now. He's the like the director of operations of the brewery. He gave us a tour of the brewery. This is what they used to filter beer. So they would take barley, right? That's a type of grain, and smash it up. They would activate it first. We won't talk about all the details. And then would let it ferment and all the sugars and stuff. That barley malt is actually really good. Like before it ferments, it's like cereal, like a heavy cereal full of proteins, and it's really sweet. It's really crazy how sweet it is. And they allow it to ferment, and then they need to filter the beer out. So they need this giant filter, right? This mash tun just went out of operation about the time we saw it. We saw it. It was already out of operation. It was in the tour, right? 1887, 1993. It's all copper. So they take all that beer, mash. It's like the mashed up wheat and everything. Throw it in there and allow the liquid to come through the bottom, and all the solid would stay up on the top. Right. So here's the thing: it's a physical process, right? Because you have the beer and you have all the stuff that's in it. It's called the wort is the mixture, but the beer and all the stuff that's in it. And you pour it on top of this mash tun, and you allow it to filter through. You're not actually changing the beer itself. Okay, the beer is still the liquid that's coming through. What determines how it separates is these grooves. This is the bottom of the mash tun. These grooves or slots allow the liquid to go through and keep the solid on the top. We do this kind of process in lab all the time, but not with beer. Sorry. I know some of you are like, oh, it's okay. You can go a day without drinking. You'll be fine. Sorry. I didn't say that. Oh, I recorded that. Sorry. So I always catch myself like, oh, I recorded myself saying that thing. I probably shouldn't have said that. We use a funnel, right? And then you can take a mixture of a solid and a liquid, for example. You could pour it through the funnel, but in the funnel itself, we have a piece of paper. It's called filter paper, which has small holes in it. And you can buy filter papers with different porosities to capture more or less of the solid. The catch is, if you can imagine, if you have to filter 1,000 gallons of beer, right? You have to let it go through. Some of the particles have to be allowed through. They get the rest of it out by other methods. But you can't make these slots too small because the liquid won't go through very fast. So the same thing with filter paper. There's always this trade-off of how good the filter paper is capturing particles versus how much time you have to do it. Okay? So we use a filter paper. This is called an Erlenmeyer flask. You're going to learn all these things in lab on Wednesday. Glass liquid funnel and a beaker, and you pour through. That's a physical separation. So when you have mixtures, when we talked about mixtures, what kind of mixtures do you have? Heterogeneous and homogeneous, right? The way you get back to pure substances is usually by a filtration method or, okay, a distillation method. And so filtration, physical process to separate a mixture. You can also use distillation. Distillation is a cool one and a hot one at the same time. You take a mixture, a homogeneous mixture usually, but it doesn't have to be, and you heat it up. You remember I said what temperature water boils at? 100 degrees Celsius. Ethanol boils at 78 degrees Celsius. So let's say you're making other things besides beer, and you want to distill the alcohol out. When you take this mixture of water and alcohol, when you hit and you heat it up, when you hit 78 degrees Celsius, the alcohol begins to vaporize out of the mixture. And so what you do is you separate a mixture because the boiling point, it's a physical quantity, physical property, right, of ethanol is lower. You can separate the ethanol from the water. So here you might have, on the left-hand side here, you could also point like this, I suppose. Oh, maybe I can't. I think I just killed this thing. No. It's very slow. Hang on. It's not even on the right slide. How weird. Oh, there we go. It's caught up yet. So here we have a mixture. Let's say it was 50% ethanol and 50% water. Ethanol is the alcohol that people drink. Over here, it could be as high as 98% alcohol. It's usually not, or 95% alcohol. It's usually not quite that high. Can't get a perfect separation. And so what happens is you heat it. You heat it here. It goes into the vapor stage, gas stage, and then it condenses. Use cooled water in this open tube, and that allows the liquid to condense. So again, vaporization, condensation, those are physical changes. And then you collect the liquid from that vapor. This is a picture that I also went, they didn't let me take, I didn't take this picture. I stole that one off the internet from their site. This is Glen Kinchy, it's a Scotch distillery in Scotland. This version you can do in lab here, sits on a bench. These are like 17,000 and 21,000 liters. And when they distill out of those things, it's like a fire hose got turned on, and the alcohol comes like streaming out. And it apparently tastes really nasty. They won't let you taste it. Anyway, it's kind of a fun thing to learn about. That's what I call a work trip, by the way. Okay, so what we're going to do, we're going to take a 15-minute break. Right, because it's now 9:30 officially. This is when lecture ends. We're going to come back in 15 minutes, and guess what we're going to do? We're going to lecture some more during the lab. So we'll take a 15-minute break. So we're talking a little bit about energy. There's two kinds of energy. I'm not going to get into the equations yet. I'll talk about those later. There's kinetic energy and there's potential energy. So what's kinetic?
It's actually moving on a line.
Energy related to motion, right? Yeah, energy related to movement. And what's potential?
Energy stored.
Stored. Oh, you read the slide.
Oh, yeah, it's stored energy.
Stored energy, right? What is potential? It means has to, sorry. It has potential. It has the ability to do it, but it's not being used. Chemistry is like chemical energy is potential energy. Because you think about fuel, and when you burn it, right, that would be carbon dioxide and water, and that's a chemical change. But so that's like chemical energy. It's stored. You get energy out when you burn the fuel. But until you burn it, nothing happens, right? So energy actually has this definition, the ability to do work. So clearly something that's moving has the ability to do work, right? It turns out work has got an equation associated, which is the force times the distance. So it's how hard you push by how hard times how far you move the thing, okay? So that's what we mean. We'll put units to these equations in a little bit so that we can understand a little bit better on a deeper level what units actually are, okay? I don't know what happened to these. I got formatted all funny when I opened it on a Mac. So kinetic, the equation for kinetic energy is E is equal to 1/2 mv squared. V is the velocity, how fast something's moving. It's squared. So that's why in football, I keep bringing up these sports things because my kids play sports, and I played a little bit when I was younger. Right? If you're running at 4 miles an hour and you hit somebody, or you're running at 8 miles an hour, you don't double the amount of energy, you actually quadruple it because it goes with the square of its velocity. That's why I always tell people don't be standing still on the field because that's, well, when you get hit really hard. Okay, so kinetic energy, energy related to motion. Potential energy is force times a distance, and force turns out is mass times acceleration. So I always like that work makes you mad. Mass times acceleration times distance. All right, so the harder you accelerate, that is the faster you get it going, that's going to require more energy, okay? So we're going to put units to them. We're not going to do it right here. So this is my daughter, Emily. This is a few years back. She's 11 now. But she was jumping on the beach, and she's at the top of her jump. You can kind of tell her because her hair is like flinging upwards, right? That's potential energy. Acceleration is gravity, how far she moves to the ground. That's the distance. You calculate how much energy, how much potential energy she has just based on how high up she is. And then she did this. Right? She converted when she fell, before I had a video camera. She fell, right? That's falling part. That's the kinetic energy. So potential energy stored up at the top of her jump got converted to kinetic energy as she fell. And then see all the water moving around? She's pushing all this water around. That's where all the energy went, and then the impact of the sand. So we convert between kinetic energy and potential energy all the time. For chemistry, we have potential energy, and when we convert it into other kinds of energy, right, it's kinetic energy. And it has to do, actually we make molecules, it's called heat. Heat is actually a form of kinetic energy, okay? Because things are moving around when you heat them up. Okay, units of measure. I put a separator slide in here because I always tend to go on too long. There's a lot that I'm covering that is review. Hopefully you guys are comfortable enough. If you need another study session besides what I'm doing in lecture, I'd like to go over this stuff in more detail, let me know and we'll put together a study session, okay? So units of measure, how we know what a number means, okay? So unit describes what a number means. The first one that we'll come across, this unit of measure, is the temperature or temperature units. Temperature is a measure of the average kinetic energy of a substance. Okay, now why does that sound weird? Kinetic energy means stuff's moving around, right? Kinetic energy is a form of motion energy. Temperature is actually related directly to how fast particles in a substance are moving. Okay? So temperature is measuring that kinetic energy. We have 3 scales that you have to be familiar with in this class. I am not going to go through and show you how to use these equations. I'm going to assume that you can do those equations on yourself, on your own. But the scales are Kelvin. This is kind of like the standard for science is Kelvin. Celsius, which is kind of the standard for everybody except us, and we use Fahrenheit. Okay? So we use Fahrenheit. So like right now, today outside, it's going to be around 100 degrees Fahrenheit. Maybe higher. I haven't checked the weather. Yesterday I was driving around in Fresno. It was 107, right? Now, in the United States, right, we assume that that's Fahrenheit. If you told somebody in the UK, oh yeah, it was like 100 today, they're like, 100 what? Because in Celsius, that would kill you, right? So 100 degrees Celsius is actually 212 degrees Fahrenheit. So we have all these scales, right, temperature scales, to measure the kinetic energy of substances. So you'll notice when just looking at this scale on the right, Kelvin versus Celsius, 0 degrees Celsius is 273 Kelvin, and 100 Celsius is 373 Kelvin. The degree, the Celsius degree and the Kelvin degree are the same size. All right? So this is for here. This is where water freezes. And the number of degrees between where water freezes and where water boils, it's the same number of degrees on the Celsius and Kelvin scale, they're the same. On the Fahrenheit scale, how many degrees is that? Right? It's 180. So that means the Fahrenheit degrees are actually smaller than the Celsius degrees. Turns out, minus 273 degrees Celsius is actually 0 degrees Kelvin. It's a temperature we've never actually gotten to. It's theoretically the lowest temperature possible. Okay? So that's why the Kelvin scale is like the scientific scale for many things, because its 0 is actually 0. 0 degrees Celsius doesn't mean 0 kinetic energy. 0 degrees Kelvin means 0 kinetic energy. There is still potential energy at 0 degrees Kelvin. You could still have stored energy, but nothing is moving. Like literally down to the electrons, nothing is moving. Sort of. So then we have the metric system. Okay, metric system, meter, gram, seconds. Seconds is the same for all the systems. Okay. Invented really by Antoine Lavoisier. Lavoisier was important because he was a very careful scientist, and he wanted units to be metricized, which means they were in even increments. So we have grams and kilograms and things like that. He also, this is right before the French Revolution, wanted to metricize the clock. This is actually a clock from the time of Lavoisier. Why does that clock look funny?
What, 10?
Yeah, there's 10 hours in the day, right? Because we have kilograms, right, and milligrams, and those things are all in increments of powers of 10. 24 hours, who thought of that? What's that?
Or then just make sure just track the when sunrise and sunset.
No, he had, yeah, well, that's maybe why our 24 hours exists. But on a scientific scale, where you want everything to be consistent on a regular scale, he did this. And then there were 30 days in every month. Why doesn't that work out? Not every
65 days.
There's 365 days in a year. You got these 5 days you don't know what to do with. So you know what they did, being French? They made holidays out of them. That's what they were going to do. And then what happened to Lavoisier is there was the French Revolution, and his other job was a tax collector. So yeah, whoop, off with the head. And that revolution and that scientific revolution, but he got enough in place that it kind of stuck. We never got the timepiece, right? There are very few of those around. That's from, if you ever go to Oxford University, they have a really cool science museum that's been around for like 400 or 500 years. They've got some crazy stuff in there. But yeah, metric system, first list of elements, quantitative measurements, and oxygen and hydrogen discoveries. Okay, we'll leave it at that. So that's the metric system. I'm not going to go into a lot into that, but it is the meters, grams, that kind of stuff. Then comes the SI, the System International of something units. It's in French. So we just call it SI units, okay? There are 7 base SI units. K, Kelvin, is temperature. S is seconds. M is meters. That's a measure of length, okay? So let me write some of these things down real quick. So this is temperature. This is time. This is length. Kilogram? Mass. Weight is unacceptable. We call it mass because weight depends on what the gravitational constant is. Mass is independent of that. But if you say weight, I'm not going to kill you over it. CDs, candelas, is brightness. Or candles. How many, like literally, like how bright is that? Oh, it's 1,000 candles. Like if you got 1,000 candles together, that's how bright it is. Which implies there's this some crazy unit of a standard candle, but I've not done much with those. So this is brightness or luminescence. Yeah, right? Mole is quantity of substance. Now mole, that's an abbreviation for mole. It's quantity. Like number of substance. And A, ampere, it's electric charge flow. Okay, it's called amps or amp. I'll just call it amps. Amp, well. So when somebody gets amped up, right, it literally means they're charged up. It's the current flow, like charge flow. Right? It turns out and it turns out like an amp is actually not a true independent unit. It's the amount of charge per second. Okay, it's actually coulombs per second. But it turns out all of every unit that you know is based on these. Okay? So just to give you a for instance, and this is where I'm going to pull some equations down. Well, hang on. Let me do it here. So, kinetic energy, we'll do it as KE like this, is equal to 1/2 mv squared. Okay? So V is velocity. Now, if we're going to do velocity, that's the distance over time, right? So what units would I use for distance? Meter. And what would I use for time? Seconds. Okay, so now when I use this equation, huh?
We're talking about Usain Bolt. He ran the 100 meters in 9 seconds.
Oh yeah. That gives his average velocity, not his acceleration.
So you can tell it's kinetic energy how much you weigh.
Yeah, his average kinetic energy because he had different velocities out through the whole thing, right? So sorry. So 1/2. So we're going to ignore the 1/2. What's the unit I'm going to use for mass? Kilograms. And what's the unit? Again, it's meters per second squared, right? So the units, just looking at units, not numbers, it's kilograms meters squared divided by seconds squares. Turns out that's the unit for energy that's known as a joule. So you could take that other potential energy equation that I gave you before, plug the units in for each of the variables, and you get joules out. So joule is what's known as a derived unit. I made it up from other units. Okay? So it's made of kilograms, meters, and seconds squared. Okay? What's the unit? Like when I look at this list, well, I look at it now and I go, of course it's not there. But when I was looking at it before and said, what's missing from this list? Volume is missing, right? So if I have a cube, how do I calculate its volume? No, yeah, but how do I calculate the volume of a box?
A cube or a box?
A box, let's say a box.
Length of the edges?
Length of the edges, all multiplied together, right? If it's a cube, since the sides are all the same, you take the length times the length times the length. But for example, if I have a box and I want to describe, and let's call this the length, this is the width, and this is the height, and I wanted the volume, I say, well, it's length times width times height, right?
Yeah.
That's a meter times a meter times a meter.
This is meter squared.
Meters cubed, yeah. You get meters cubed. That's a unit of volume. A unit of volume is a derived unit. Okay, so relatively, meters cubed is not that important. I'll talk about prefix. I'll come back to it in a second. Go back to this one. So there's all kinds of ways, though, you can calculate a volume, right? It's the length times the width times the height. An area is the length times the width. We'll get back to that sometime maybe. But if it's a sphere, and you want to calculate the volume, right? It's not length times width times height, right? Because it's a sphere. What's the length times width times height? It's 4/3 pi r cubed. But this is still, right, a radius times a radius times a radius. So you get a cubed length unit, and it's still a volume, okay? So any three lengths multiplied together will give you a volume. Now, an important aha moment, I think, for a lot of people is this one. If you take, that thing's bigger than 10 centimeters on the screen, right? If it was 10 centimeters on the side, you'd be like hard to be able to see that. It was like this thing. But that was a 10 centimeter on a side cube. And I take 10 times 10 times 10, what is that? 10 times 10 times 10, don't pull out your calculators. 1,000, yeah? Shh. 10 centimeters times 10 centimeters times 10 centimeters. That's going to be 1,000 centimeters cubed, right? That's a liter. The definition of a liter is 10 centimeters on a side cubed. So that's where we get this unit of volume. It's actually derived from centimeters. So there's 1,000 centimeters cubed in a liter. What else are there 1,000 of in a liter? Milliliters. What does milli mean? Milli means 1,000th, right? So it's 1,000 thousandths of a liter. That's a liter, right? So that means a milliliter is 1 centimeter cubed. And that's where we get the definition of a milliliter. It comes from our definition of a liter. And if you've done hospital work or health work and you have to give injections, they don't usually say milliliters, they usually say cc's. Those are cubic centimeters because a milliliter is a cubic centimeter. Okay, so in addition to, SI units, we can talk about big numbers and little numbers, large and small numbers, using what are known as prefixes. And prefixes simply replace exponential notation. Okay? Or powers of 10, because exponential notation, or scientific notation, is representing numbers in powers of 10. These you have to memorize. These are the ones, the book has a longer list. I gave you the short list, okay? So, giga, like a gigabyte, 10 to the 9th, it's a billion, okay? Now, a gigabyte is not actually a billion, but whatever. Don't take it too far. With the computer guys, like a kilobyte's 1,024.
Space 80.
Yeah, it's like, thank you very much. Okay, but a mega, like mega man, megabyte, roughly, and mega exactly, 10 to the 6th, it's a million. Kilo is 1,000. Deci is 1,000. Right, and go down the list. You guys are probably familiar with centi, because how many pennies, right, are in a dollar? 100. And what do we call them? We call them cents. Right? So hundredth is a centi. Milli is 1,000. The thing that's the only weird part, these are not all of them, there's a few others, are these deci and centi. Everything else is in powers of 3. So I have milli, micro, nano, pico. When you get to the order of pico, you're getting on atomic. If it's a meter, picometers, we're approaching, it's the atomic scale. Okay, I think carbon's like 70 picometers in diameter, the atom. Okay. Femto, 10 to the minus 15, and then there's atto, and then, you know, there's stuff below that. There's yocto, and anyways, we're not going to go. Zepto, there's other ones below that. That's what those represent. So if I have a number, and I say it's, let's say, let's pick on micro, 35 micrometers. I just use a length. Prefixes can be used with anything. You use with mass, length, time. You have microseconds, milliseconds, right? The Olympics are splitting times with milliseconds. 35 micrometers actually means 35. I'm teaching you how to do your first conversion. Times 10 to, what is micro? -6 meters. That's all that means. Now, if I want to, that's converting to exponential notation. If I want scientific notation, I always put the decimal between the furthest leftmost numbers. So I would have to take this, and I would have to drop it over here. That would be 3.5 times 10 to the minus 5th meters. Okay. On the other hand, if I had, let's say, 0.003, my pen is skipping. Hang on, let me try something. I'll pull out the other pen. The styli get funky after a while. I guess that's plural of stylus is styli. I don't know. 0.0037 grams, and I want to know that in milligrams. Actually, if I move this over 1, 2, 3, that's 3.7 times 10 to the minus 3rd grams. What is 10 to the minus 3rd? Oops, sorry. Why do I have an alarm going off now? What is 3.7 times 10 to the minus 3rd? What's the 10 to the minus 3rd? Milli, minus 3rd, not plus 3rd. So it's 3.7 milligrams, okay? The purpose of having prefixes is so you don't have to write scientific notation, but sometimes you need to go back to scientific notation so that you can use the numbers in calculations. Simplest way to convert things is just by replacing them, okay? I'll show you a more systematic way in a little bit. Thing I always remembered when you're moving the exponent is red lay, right exponent goes down. left exponent increases. Took me a long time to think of that, by the way. I'm sure somebody else thought of it too, but we all reinvent our wheels. So if I'm going to convert this to megawatts, all right, this is a lot of watts, right? I have to go like this. Oops, hang on. Dang it. Man, the internet's so slow in this room right now. I have to go from the decimal being here, 1, 2, 3, 4, 5, 6. That's what mega is. It's going to be 10 to the 6th. And I'm moving it to the left. Right? I'm moving the decimal from where it is to the left. Left, you increase the exponent. So megawatts, that's just going to be 20.15 megawatts, like that. If I'm going from grams to milligrams, milligrams 10 to the minus, milli is what?
-3.
10 to the minus 3. So I have to take this decimal 3 places this way, 1, 2, 3, right? So that's what this means, red, right, exponent decreases. So I'm at 10 to the minus 3 now. So in terms of milligrams, that's 11.5 milligrams. If I'm doing 1250 milligrams to grams, right? Now, this is a little trickier. It's in milligrams. That's minus 3. So I have to move the decimal left to get it to go from minus 3 to minus 2 to minus 1 to 0. Yeah, so this becomes just like this. 1, 2, 3. That's 3 places. That takes care of that. That's 1.25 grams. So I can do the same thing with 3.5 micrograms to centimeters. It's a little trickier, but micro is 10 to the minus 6. Centi is 10 to the minus 2, so I have to move it 4 places, okay? And I'm going to have to move it because I'm going from 10 to the minus 6. By the way, there's slow ways to do all this too, by the way. I can show you the slow ways. Because they're easier to remember how to do rather than trying to hold all this stuff in your head. But I'm just trying to show you can do this really quickly. We're going from 10 to the minus 6, 10 to the minus 2, so I have to increase the exponent, so I've got to move the decimal to the left. So what that means is I'm going to have to go like this. I have to pretend that there's zeros out here and go like this. 1, 2, 3, 4, because I got to go 4 exponent powers up. And so now this becomes 0.000350 centimeters. Oddly enough, that's a conversion in grad school I had to do all the time, and I screwed it up all the time because I always in my head thought, oh, it's powers of 3, but this one's powers of 4. So, yeah. I made electrodes that were 1 micrometer in diameter and implanted them in rat brains. 1 micrometer is really small, and I made them by hand. I drank less coffee, and I had a microscope and a lot of small tools. So, okay. I talked about the derived unit already, so we'll skip past. This I already talked about, so I'm going to skip this slide. So we're going to talk a little bit about measurement. Before I end today, I got to talk about converting units. I may not get to chapter 2 today, but the way the syllabus is outlined, right? If you look at the syllabus, the day the chapter is listed is when I start it, not when I finish it, okay? In case you were freaking out. Okay, science is empirical, so it's based on measuring, and if you measure it, then you believe that number, right? So, but here's the problem. Every time you make a measurement, there's uncertainty in a measurement. So what we have to learn in chemistry is how to understand how to deal with uncertainty. In the lab that we do next week, we're going to do that mathematically, okay? For now, we're just going to do conceptually. So when you make a measurement, you always get a number, and you get the units. Like I said already, the units are what you are measuring. It gives us meaning to the number. And this uncertainty is what makes the picture not clear. Okay, so now I know that's not clear in itself, so what I'm going to do is give you a little short example. this is how you read a graduated, you could put a lot of different things in there. A graduated cylinder, a burette. You guys should be familiar with these types of measurement devices. So this is what we're going to do. We're going to try to figure out what that volume is. Okay? This is how I'm going to do it. We're going to do it by voting. So for sure, the number that you're looking at is between 4 and 5. Can we agree on that? It's 4. By the way, I don't write everything on the board up here just because I like chalkboards. You got to come to class for something, right? So if you look at the gradations, this is 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 10, right? So those big lines in between the biggest lines are tenths. So when you read a liquid inside a graduated device, you always record it based on the bottom of the meniscus. This is known as the meniscus. When you look at the liquid, it curves at the bottom. This is clearly between what two numbers?
0.5 and 0.6.
Yeah, it's between 0.5 and 0.6. So the next number on my measurement has to be 5. Right? Those are my certain digits. I know those for sure. Right? Now it comes down to this. It's between. Now we're in the hundredths, right? So that number, let's say it's 2, 3, 4, 5, 6, 7. It could be any one of those.
I think it's 7.
Oh, sorry. Let's do 8 too. Yeah, because I want to give it a little bit of range around where it's at. So who thinks it's 2? Who doesn't want to raise their hand so I know what I'm dealing with? Okay, you don't want to raise your hand? Good. Is it the 3? Because the 3 would be below halfway, right? 4 would be below halfway. 5 would be right at halfway, and you can see it's actually a little bit above halfway. Now, 6. How many people think it's the 6? Yeah, maybe. I get 2 votes for that. 7. I get, wow, everyone else. How many 8? So you notice we didn't pick the same. It was about 50-50, 7 and 8. Huh?
I said I'd call it half 7.5.
Yeah, no, we can't do that. Because you can't.
1 unit of uncertainty.
Yeah.
Yeah, that's the uncertain digit. So how many of these numbers are certain? Well, the 4 and 5 are certain. The 7 or 8, that's the uncertain digit. We don't know for sure. So if I wrote 7, that would be right. And if you wrote 8, that would be right. Except I'm the teacher, so it's 7. No. So that's the thing about that last uncertain digit. We're going to record it differently, especially on a device that's analog. Analog means digital. What does digital mean? Computers, but it represents actual numbers on the screen. Like if I measured this volume on a digital device, it would say it's 4.57, and then you would say, well, it must be a 7 because the instrument says it's a 7, right? But this is analog. You're doing it. Oh, it's augmented reality. How's that? You have to interpret on top of the digital world what's going on. It's like the Pokemon, you know, that's augmented. You know, we have gyms on either side of our, I don't know why they did this, but there's a gym on each side of our building and a Pokestop. I think you can actually get it from here. Now I know who's playing in class. Okay, stop doing that. So 4.57, okay? The significant digits are the ones you know for certain and the first uncertain one. The one that we're kind of guessing at, but you know, it's not a complete guess because you know it's not these, right? So I have 3 significant digits in here. Okay, that's the idea of what we call significant digits. It's trying to figure out the numbers you know for sure and then the first uncertain one. Now, if I give you this number like this, 4.57, you have to assume that these two are the first certain ones, and that's the uncertain. So I have 3 significant digits that way, too. When you're recording it, you record everything you can see for sure, and then you estimate one. Okay? It's often referred to as the estimated digit.
That one's subscripted sometimes when you note it?
No, I don't do that. I think some people do. Like they'll take this 4, 5, and then drop the 7 down. Right? Now, the thing that's missing from this is it's in milliliters, so this is ml like that. So when you record a number in the laboratory, which is what you're going to do a lot of this semester, you write the number and you write the units, and you write the numbers so that you represent the certain digits and the first uncertain digit. Okay. What about that one? So I stole this one from a friend of mine who now passed away many, many years ago, but he had this in his lab manual that he wrote. This is how far we've come in. That was his illustration in his lab manual. So this one, what would you say that one is? We can agree on the 15, 16.
Oh, it's an increment.
So what's it in increments of here?
1.
There's 5 spaces. So they're increments of 1, right? So this is 16, 17, 18, 19, and 20. So we can all agree that this is what? 18. Yeah. But is it on the line?
No.
But it's close, right? So I can estimate that that is a 0, but I can't do anything better than that. All right? Or I could say an 18.1, and we might agree on that too, right? That's okay. This is the process of science. We make measurements. Not everybody's going to see the same thing, but then we interpret our results. We know how much error is in our results, and we can agree to disagree on that value. Okay? Yeah, it's kind of like peer review. Yeah, it's the peer review process. This internet's killing me. I can't point us. Okay. All right. Okay, so don't forget, like if it's right on the line, this is a classic student error. The thing that I see all the time, okay, is they'll write 18. All right? That means you're not sure if it's an 18, a 19, or a 17. That's what 18 means. 180 or 18.0 means it's 18, and I don't know about this little bit of fluctuation here, not this fluctuation here. Okay? So the range for this number, another way to think about this is range. This can go from 18.1 to 17.9, whereas a number like 18 goes from 19 to 17. And clearly you're not that bad, right? So, and then the unit that describes this is in milliliters, so I'd have to drop a milliliter after that. You might record that, I might record, whatever. It works out. Now, this is what I was talking about. This is analog, right? This is digital. What are you going to record when you see this? 10, 0, right? 1, 0.2. Nobody's going to look at the 2 and say, well, that could be a 3. Well, you might. And nobody's going to look at this number and say, well, that 0 is clearly not a 0 because it's a 0. What else could it be, right? So if it's a digital device, just record all the numbers that you see. These guys are digital. Not these guys. These guys here. These people are actually analog. But these are digital. And if you look at the screens, they don't have a scale that rolls up and down. Now, when I was in college, it was actually a scale that would roll up and down. And you had to read between the lines. Yes, those were the good old days.
Card catalogs in the library.
Yeah, you know what's good about the good old days? They were the good old days. Things were always harder. Almost always harder. But somehow they're more enjoyable. When you go to the library, you can just pull books off the shelf. You can just kind of go through journal articles. I still enjoy doing that. Or telling my son, hey, give me that journal article. He gets it for me. Oh yeah, so my oldest, a little side story, my oldest is in grad school now. He's getting his PhD in chemistry of all crazy things. And my youngest is 7. He's going to be in 2nd grade. Got this big span. I lived the life. Okay, so let me talk a little bit about significant figures, okay? How many significant figures on the left here, by the way?
4.
It's actually got 4, and I'll talk about that in a second. And this one's actually got 3, okay? So here's the thing. There's this thing that we call absolute precision, okay? If I had recorded this number, I only put these zeros here because I had to have placeholders. But if I'm looking at this, the absolute precision here is 100. Because it can be 1074, 1076. That's 100 every time I make that change, right? This one, the absolute precision is in the ones place. So it could be 164 or 166, okay? So absolute precision, in this case, on the left is in the hundreds. Let me try this again. Yeah, it's just dicey today. And this is in the ones. But in terms of relative precision, all right, this number is good to about 1 part in 1,000. And this number is good to about 1 part in 100. Okay? It doesn't matter how many zeros I put here. It's still, if this is the last significant, the first uncertain digit or the last significant digit, it's always going to be good to about 1 part in 1,000. So that's what we refer to as relative precision. And when you multiply, so this is where it's going to be important. You guys all learned the sig fig rules, I'm assuming, at some point. So this is kind of supposed to be reviewish. When you multiply numbers, or you do anything that looks like multiplication, like squares, square roots, it's always the relative precision that matters. So you're always counting the number of significant digits in a number and using that to determine where you round your answer. Okay? On the other hand, when you do addition and subtraction, it's the absolute precision that matters. Okay? So let me break this down. This is about 1 in 1,000. And, you know, this is really crude to say this, but this is about 1 in 100. Because actually 1 in 165, right? But when we do sig figs and rounding, we're approximating relative precision. Okay, so let me talk about accuracy and precision real quickly. So I'll give you a definition of accuracy, okay? I'm going to write it out, and then I'm going to ask you to tell me what's wrong with it. How close? So accuracy has to do with measurement. So you measure and you record a number, okay? So how close a value is to the known value? Accuracy is how close a value is to the known value. Why does that sound weird?
Well, I mean, you don't always have a known value.
Yeah, why are you measuring it if you know it? That's why it sounds weird, right? But sometimes you want to know if something is the same as something else, right? So you're measuring to see how close this object is. Like, if I wanted to measure how tall every woodchuck, I don't even know what a woodchuck really looks like, but if I wanted to know how tall a woodchuck was relative to another woodchuck, there isn't an absolute known value for that. But if I wanted to know, like, how closely a penny mass is to what the mint says the mass is supposed to be, because they've made the penny to be a certain mass, right? I couldn't have a known value for that penny. Go ahead.
And also, like say, these penny example too, there's also, you can also check if the penny, well, there's always imperfections.
Yeah.
Anywhere, so you can always check if it's actually.
Yeah, so do the pennies in production match the pennies that are out in the environment when people use them? Or if you want to know how close something is to a particular velocity, you can measure how fast it's going in comparison to this is the known velocity of an object, like the speed of light. How close is it to the speed of light, right? Speed of light, by the way, right, is always the same, 3 times 10 to the 8th meters per second. Okay, so that's how close the value is to the known value. Catch is you have to know what the value is, and for some things there isn't a set known value. That's what's weird about the definition. And why would you know it? Why would you be measuring it? Because to make comparisons, okay? On the other hand, and you do this a lot in lab, by the way. I'll give you an unknown, and you have to tell me how close it is to the known value. We make the samples, you analyze them, and you report the results back to me, and your accuracy is what determines your grade, okay? The other thing that would determine a grade is precision, okay? So this is kind of a weird thing. How close measured values are to each other.
Presumably the same sample, right?
Yeah, hang on. I want to make sure I finish writing.
Sorry.
That's okay. Yeah, presumably you're measuring the same thing. So I could take something and weigh it on the balance 10 times. It turns out I'll probably get 6 or 7 different values for the same thing that I measured. How precise the measurement is how close those values are to each other. How accurate it is how close those values are to the actual value, which I may not have, right? So here's the deal. You want to be very precise in all your measurements, because if you're not, you can't determine whether or not you're being accurate. Precision is how good you are at replicating a measurement, how good you are doing the same thing over and over and over again. Okay? So, throwing darts. I used to throw darts in college when I had nothing better to do. This was actually graduate school. Somebody got me into throwing darts. Here's a dartboard. Okay, it's a simplified dartboard. So, assume I'm throwing at the middle of the dartboard. You don't always do that, but just assume, okay? And this is where the darts show up.
Accurate and precise.
Accurate and precise. They're all in the ring. Well, they're supposed to all be in the ring. All in the ring, all close together. Throwing for the middle, I hit the middle. They're close together, okay? And then the wind blows, and they all end up like this.
Precise but inaccurate.
It's precise because the values are close together. It's like getting the same mass measurement repeatedly, right? But because there's a systematic error, that's what this is showing me.
Which is the wind, right?
Which is the wind cutting across my throwing field. Right? I have a systematic error. All my measurements are going to be skewed to the right. Okay? But it's still precise because I got all those points together. Now here's the thing in science. You're throwing darts. You don't know where the board is. So in lieu of not having a board, you just make sure that all your measurements are close together. Now, let's say you've had one too many, because you guys know most of the people throw darts in bars. I always said this is a bad combination.
Sharp objects and alcohol.
Throwing sharp objects. And you do this. What's that?
Imprecise and inaccurate.
Imprecise and inaccurate, because you don't know, like maybe he was throwing over here, but maybe there would have been a fifth dart, it would have been over here, and it would have been right in the middle. So one of the things that you have to think about in science is we're trying to make precise measurements all the time, but we don't have the dartboard. We're throwing darts, we're trying to make measurements repeatedly the same way, but we don't always know what we're trying to get to. But if you don't throw precisely, if you don't make precise measurements, you can't make any conclusions about what the value is. One of my projects in graduate school was to work with a group of guys. We were working together to try to find, guess what a neuron is? Right? A neuron has neurotransmitters in it. What are the neurotransmitters packaged in? Anybody remember this from biology? Starts with a V. Vesicle. Yeah. On the tip of your tongue, he's like, hey, biology, I'm going to wake up. Vesicle, right? Our job, we figured, we had the first direct chemical measurement of neurotransmitter content in a vesicle. And we could measure thousands of them at a time. So we would stimulate a neuron, and we would get the neurotransmitter released, and we would quantify each one. Now, let's say we weren't very precise in this measurement, right? Our number, our mean quantity of dopamine or norepinephrine in the vesicle would be relatively meaningless if we didn't make precise measurements. But because we made that measurement, and we're like one of the first people to publish it, right? That number stands as the number, right? And people rely on that number because we made the measurements precisely so that other people could replicate the result and say, yes, that's what that number was. Now we're going to do it. Now that we have the technique done, we're going to do it on something else. Okay? So we did adrenaline. Right? It's called epinephrine is another word for adrenaline. We did adrenaline and adrenal chromaffin cells, and we determined the amount of adrenaline in every vesicle and got a distribution of sizes, that kind of stuff. It was good work. I was a name on the paper. I did all the analysis part. And some of the getting, when you do stuff like that, you actually have to have tissue from like an animal. So we went to it was from cows, so we would go to the place where they butchered cows, and we'd have to stand there and wait for the guy to pull the organ out and hand it to us. It was like weird. And we have to shot juice in them and tied them up, threw them in an ice chest, and went roaring back to lab.
You did some steaks while you were there.
No, it was not part of the. There was a research group at North. There was a research group in North Carolina that did neurotransmitters in the antenna of lobsters. So they needed the antenna from the lobster.
Well, the rest of it.
The rest they threw in a freezer to dispose of later. And at the end of the year, at the end of the school year, they would get rid of all that extra lobster. Yeah, that was a pretty good deal. Okay, so let's talk a little bit about sig figs. I'm not going to go over the rules, but I'm going to go over, we're going to just practice some of this real quickly. So in terms of significant figures, every digit that's recorded is a significant figure. So how many sig figs in that number? 4. All right. Any zero is significant as long as it's between two numbers. So this one has 4. Now, here's a rule. This is kind of arbitrary, so kind of pay attention here. If it doesn't have a decimal, the zeros that are to the right, they're called trailing zeros, don't count. If there's a decimal in the number, before the number, to the right of the number, every zero counts to the right. Okay? So, do I have a decimal here? No. The book would say this is ambiguous then, and it is, because somebody might have meant to put the 0 there. So how many sig figs is in this then? 3. These don't count because they're to the left, so leading zeros never count. So there's how many here? 2. And how many here? 3, yeah. Good. Okay, so when you multiply two numbers together, it's the relative precision that counts. That means you count sig figs. So if I do this calculation, this is what I get. All right? There's how many sig figs in this number? 4. These are the numbers I looked at before, by the way. Wow, this is really, it's really slow right now. That's 4. 165, how many sig figs in that? 3. So this number, the relative precision of this number can't be greater than that number. It's like saying this number is going to be better than the thing that made it. It's not like your children. Your children will be better than you, right? Okay. But in this case, this is like saying my children can't be any better than me, which would be a sad state of affairs, honestly. So I have to have 3 sig figs in this number, and then you round. Okay? If this is the last calculation, I round this number. I would say that's 1, 7, 7, and then I have to have 1, 2, 3, 4, 5 zeros.
In that case, wouldn't you just do that one in scientific?
I'm getting there, getting there. So I go to scientific notation because nobody wants to look at that number. So that's 1, 2, 3, 4, 5, 6, 7. So 1.77 times 10 to the 7. That was fortuitous. I like all those sevens. It must be good luck. One of the things about scientific notation that's cool is it gets rid of these zeros that are ambiguous. That's the train making the thing shape. Okay, now, when you add numbers or subtract numbers, so this is multiplication, division, powers, and roots. Like squares and square roots all follow this rule. I can't stand when it vibrates like this. When you do addition and subtraction, it goes on the absolute precision. So let me show you why that is real quickly. If I take this number and I say I'm going to add 165 to it, most of you would do this. Right? Or you throw in your calculator, but this is what you're doing mentally. And you get this number over here. Well, if we're following significant figures rules, this 5, right, is uncertain. It's got a little uncertainty. It's a 4 or 6. This number, what do you know about it?
It is completely uncertain.
It's completely uncertain. It's a 0 for holding a place, but you don't know what this number is. So let me ask you, when you take something you don't know and you add it to something you do know, what do you know?
Something you don't.
Something you don't know.
You don't
right?
know it.
You know mathematically that that's a 6. You know mathematically that's a 5, but it's a 6 plus could be lots of things, an unknown number. So what we do is say, well, I know, right? I know that this number was a 1, and I know that that number is a 5, so that's where I'm going to round that number to. Over here, I don't really know what these are, so I can only use these in the math, and then I get rid of them when I round it. Okay?
So it'll be 107,700.
Yeah, 107. 107. This is the last digit based on the absolute precision. 107,700. Okay.
So it would be 1.077 times 10 to the third.
Yeah. Yeah, 1 point. And then again, numbers like that, nobody wants to look at those trailing zeros. Like that. Okay? Good. So let's do one real quickly. I'm multiplying, so it's relative precision that matters, right? So I want to calculate the area of a rectangle that has a length of that and a width of that. So I want to calculate the area, so I take length times width. This number comes out to be, turns out to be 3375 centimeters squared, because I multiplied the centimeters together, right? How many sig figs in the numbers going in?
3 and 2.
This has got 3, and this has got 2. And so this answer can only have 2, so I round it to that place there. So that becomes 3.4 times 10 to the third centimeters squared, okay? So basically, I mean, application is a lot easier to think about. Just count sig figs. When you're multiplying, you just keep the sig figs of the number with the least sig figs. Right? As a graphic, as an image, just look at your two numbers. Whichever has least, that's what you keep. Sometimes it's easier to see the rule than it is to say the rule, right? You don't. I might ask you to write the significant figure rule for me for addition, subtraction, multiplication, division. Probably not. But if I do, just use your own words, like give me an example and say, this is how it's done. But good, you get it. So I've got a beaker, and I've got 7.75 milliliters stock solution, added 93 milliliters of water in a beaker, right? Calculate the total volume. Well, you guys kind of know how to do this, right? So I'm going to take 93, oops. Sorry, the pen is skipping a lot, but that's a lot to do with the slowness of my internet here. Or the herky-jerkiness of my internet here. So it's the absolute precision that matters, right? So this is what I tell people to do. You look at the two numbers you have. That's the least precise, right, place. That's where I'm rounding to. I'm rounding to the ones place. So this becomes, when you add all this up, when you add it together, you're going to get 100.75. I picked the numbers intentionally to make the math easy for me, and I still had to look. Milliliters. But that's the last place I knew all the numbers. So I'm going to round to that, so it becomes 101 milliliters. Good? What happens? I seem to have misplaced the other pen. The other pen was working better, but then I always put these things down in funny places. Yeah, well, whatever. Figure it out later. Oh, wait, a second in my back. I'm doing the Macarena, actually. I usually just say what's on my mind, which is kind of bothersome to me, but. So, a little bit harder problem. A cube is placed in a graduated cylinder containing 25.3 milliliters of liquid. The new volume, that is the cube plus the liquid, is 32.57 milliliters. If the mass of the block is 83 grams, is the block made of lead? That's the question. Okay. Now, you guys know what density is? It's the mass of an object divided by its volume. So what we're going to do in this problem is calculate the density of the object. So density breaks your heart if you don't know that one. It's the mass divided by the volume. What's my mass? You guys get it now? Yeah. The mass is 83.00 grams, right? What's the volume of the block? Yeah, this is the volume with the block and the water. That's the volume of the water. This is known as the displacement method. Based on how much volume the block displaces in the liquid, you can calculate the volume of the block. So the volume is 32.57 minus 25.33 milliliters. I'm being lazy and writing it at the end. So what do you get? 7.24. Yep, 7.24.
Which would reduce the number of sig figs, right?
So let's look at this real quickly. So this number, froze up on me. This number is good to the hundredths, and this one's good to the hundredth. When I subtracted it, I lost this tens place. So even though these have 4 in them, I've tracked this down to 3 sig figs. Okay, so when you do a calculation like this, right, I calculated now a number that has fewer sig figs than I started with. You have to keep track of these things. Now when I get the answer, I can just do this, divided by 7.24, and I end up getting, somebody whip that out for me really quick.
11.46.
11.464? Hang on. Grams. Oop, I left my milliliters up. Per milliliter. Okay, so now, how good is this number?
Good to the tenths place.
When I did the subtraction, I did absolute. When I do the division, I got to track the relative. So I got 3 sig figs here. I got 4 here, so this number has to be 3 sig figs. So I get 11.5 grams per milliliter. Now, is it lead?
Yes.
Maybe. It matches the density of lead. Now you're going to look, that's a trick question. I did that intentionally. I love it when people say, yeah, it has to be. I'm like, well, there's a lot of things that could have that density. All right. So 11.4 versus 11.5, within significant figures, that's the same number. Because 0.4 could be 0.5 or 0.3, and 0.5 could be 0.4 or 0.6. So they actually overlap each other so that these two densities are essentially the same, but you can't say for sure that it's lead. It just possibly lead because the densities are the same within significant figures. You'll see this all the time in science. You'll see somebody say, I got this number for this. Somebody will say, I got that number for this. And they're different numbers, and they say, we agree. All right? It has to do with how much error is in a measurement.
So you're saying though, it might be something else, so it could be like bismuth and gold.
Yeah, it could be a mixture of two things that turns out to be a gray, soft, shiny metal. Yeah. Of course, you could eat it, have neurological diseases, and then decide, yeah, it's lead, or you can just test it another way. Yeah. We actually have, there's lots of ways to test it, determine if it's lead, because you could just send it in and somebody will tell you if it's lead, because lead is such an environmental problem that we have because of lead-based fuel, lead-containing fuels that we burn for like 100 years. Yeah.
All along knowing they were contaminated from doing it anyway.
Yeah, that's a long story, but it's true. So this is what I'll do. I'm going to stop here. I didn't actually get all the way through, but I'm letting you out early for a reason. One is the lab coats. Okay? So I'm going to go get the lab coats.